So the speed of light is actually constant, and that doesn't fix everything else. Now, this actually sounds a bit screwy at first, the fact that time can slow down, or that length contracts, or that the mass increases. All these sort of things do sound a bit strange, but they've all been verified over the last 50 years or so. For instance, the idea that time slowing down has been verified back in 1971 by two physicists that booked 4 round-the-world trips consecutively. And they actually took 2 atomic clocks and they circumnavigated the Earth. But they were able to notice to within 10% that Einstein's model was actually correct. What's one of the things in terms of modern day technology where you need to take account of that kind of small difference in time for, say, things orbiting the Earth? Okay, so for global positioning by satellite system, the satellites are rotating around the Earth. They deal in very small increments of time to work out where you are on the Earth. And in that case, special relativity has to be taken into account in that timing system. So this isn't science fiction. It's not something where people are saying, oh, well, it'll probably happen when you get close to the speed of light. It's observed, and it's part of everyday modern physics. So as something gets close to the speed of light, there's a couple of things happen. We're going to look at the main one that you need to know about for advanced higher is mass. What happens to something's mass? When you start at a rest speed here, if you plot the mass of an object, the mass is obviously the mass that it has. We'll call that m0, which is the rest mass. So if we're taking a kilogram, and a kilogram is at rest, our kilogram has a mass of a kilogram, end of story. It doesn't, that's what it is. As you get faster and faster, very little happens. I mean, very little. Certainly, my car going up to 70 miles an hour, virtually nothing happens. And then, suddenly, and then very suddenly, the velocity, as the velocity increases to approaching the speed of light, the mass suddenly increases. So you've got very little happening until you're close to the speed of light, then a sudden increase in the mass there. The mass, which you're actually measuring here, is the relativistic mass. And so the relativistic mass of something is going to be equal to the rest mass when it's not moving anywhere. But as soon as you start moving close to the speed of light, and we'll find out how close you've got to be to the speed of light, that becomes bigger. And there is a factor which you multiply the rest mass by to find out how much bigger relativistic mass is going to be than the rest mass. What's the factor, Kirsten? Okay, Lorentz factor. So what you're going to do is multiply by a factor which is 1 divided by the square root of 1 minus the speed that you're going divided by c all squared. And that 1 over the square root of 1 minus v over c squared is the Lorentz factor which I asked you to have a look at. So that's the good news is that equation, firstly, you don't have to derive it. Believe me, you are glad you don't have to derive it. And secondly, it's given even in the exam paper. You don't even have to look it up in the formula books and data books. It's actually part of the course that you're only supposed to be able to work with this formula if it's given. However, it is quite a tricky formula. So we're going to try a few bits and see how fast you've got to be going for the rest mass to become any different to the relativistic mass. So if we take, if you take your own mass, and I'd like you to calculate your own mass at these following speeds. If you're not sure what your own mass is, just take it to the nearest sort of 5-10 kilograms. You're going to be something like 60 kilograms, something like that. So just take, for example, I think I'm currently about 80 kilograms. If I was to try and work out my relativistic mass at, I don't know, how fast would you like me to go? Just sort of dial up on the scale of sort of 0 to 3 times 10 to the power 8. How fast you'd like your teacher to go? I mean, this isn't going to be practical. It's just a thought experiment. Before you get this idea, I'm going to be shot out the window close on light speed, appealing as it is. 600,000 meters per second. Okay. And so if my mass is 80 kilograms, Anna's just shot me out at 600,000 meters per second, which I think is about as fast as any manned space exploration device has ever gone. Sorry, not even a manned one, but I think that's like Voyager's speed there. How much my relativistic mass would be if that's the rest mass. So the relativistic mass is going to be 1 over square root of 1 minus 600,000 divided by 3 times 10 to the power 8. That's all going to be squared inside that bracket, multiplied by 80. So when you're calculating this, on your calculators, work that out first, square it, do a change sign, add it to 1, or use your brackets, take the square root, then do reciprocal. You've got to work from the inside out. It's such a complicated formula, I wouldn't try just doing the whole thing with brackets. I would work inside out. We'll see how well you do. So try that now. So you can see how it's even 600,000 meters per second, which is only a very small proportion of the speed of light. We're still bumping along at this part of the graph. Try this time sending me out at half the speed of light, at 1.5 times 10 to the power 8. Do the same calculation, this time 1.5 times 10 to the power 8. Let's see how much my mass is increased by in that case. But what I'd like you to be able to do now is to get your own version of that graph there. So I'd like you to plot a graph of, you can either use your mass or you can use my mass, but work out what the mass would be for every 1 times 10, every 10th of the speed of light. So you'll go along, and that'll be 0.3 times 10 to the power 8. That'll be 0.6 times 10 to the power 8. And every 10th of the speed of light, you'll go and try and work out what the relativistic mass is. So you'll have 10 points on your graph, and we'll see whether we're getting that kind of curve there from that equation. So there's 3 different aspects of energy in terms of relativistic energy. The total energy is your mc squared energy. So at rest, and that's the same energy that you were working out last year. At higher, you were using mc squared for changes in mass in nuclear reactions. When it starts moving, though, so close to the speed of light, the relativistic energy adds to that, and you get into total energy with mc squared, where that's the relativistic mass. But that's a total energy there. So the difference between the two is the energy due to the movement. That's the extra due to your relativistic mass being bigger than your rest mass. So we'll just call it, in speech marks, kinetic energy is equal to the total mRc squared minus the rest mass times c squared. So whatever energy you've got, because you're traveling at close on light speed, your mass is increased, therefore your energy is increased, and you can subtract your rest mass relativistic energy from that, and that will give you your kinetic energy as you approach light speed. So we're going to use the equations for relativistic mass, which was that you take your so we're using relativistic mass is your rest mass multiplied by that factor, the Lorentz factor, which was 1 over square root of 1 minus v over c all squared. That was the Lorentz factor which you had last week where you plotted the graph. That equation itself, if I rewrite it this way, you'll see why I was referring to the binomial expansion before. it's going to be m0 1 minus v over c squared. To what power would that be? Instead of 1 divided by the square root of that lot. Yeah, Chris? Negative a half. So it's minus 1/2 there. So we've got, if we compare that to the 1 plus x to the power n general equation for the binomial expansion, can we use the general binomial expansion with that to expand out that bracket, even though it's to the power minus 1/2? Pure math says that we can, so that's what we'll do. Okay, so we're going to use the rest mass times 1 minus v over c all squared to the power minus. At this point, we put our physicist's hat on and say, well, cut to the chase, what really matters here? And the thing which really matters is what's happening when light speed is so far in the distance that when we're traveling at a speed much lower than light speed. So when v divided by c is actually much less than 1, in other words, that our speed is much, much less than light speed, can we take that and find out what this would be as an approximation? Well, v squared over c squared all squared, if that's much less than 1, that term there actually starts to become very close to 0. Say if this was, if we're traveling at 100th of the speed of light, v squared, v over c squared would be 0.0001, v squared over c squared, v over c was 0.01, v squared over c squared would be 1,000th. By the time you square that, what are you going to end up as a fraction? Even smaller, it's going to be so v over c squared all squared is going to be 0.000000. We're already into millions. It is not significant. So any terms past this one here, we can ignore as an approximation. All we're interested in is that this, at anything in our sort of existence at less than light speed, is equal to 1 plus 1/2 of v squared over c. So the kinetic energy is, so going back to what we had here, plus 1/2 rest mass v squared over c squared times c squared minus m0 c squared. That equation then simplifies considerably. What does it simplify to? Try it yourself and see. Rest mass, relativistic energy m0 c squared minus m0 c squared, they cancel. 1/2 m0 v squared over c squared times c squared becomes 1/2 mv squared. We have managed to, from the point of view of total energy of a moving object, taking into account the relativistic energy and its rest mass energy, move it at a speed close on to light, so nowhere near light speed, with v much smaller than c, and by expanding out that term there, ignoring anything which becomes close to 0 because of that assumption, you end up with this equation here. And surprise, surprise, the kinetic energy of something traveling at nowhere near light speed is 1/2 mv squared.